Okay, so this is applications of graphs. So it's the same stuff you've been doing. You're going to take this graph, this function, and graph it, and you're going to find the max and min values. That's what these applications are looking for. Sometimes they'll ask for increase or decrease. For most part, it's the max and the min. So on this one, you can go right to the end and say, it says, what is the maximum profit? So what you want to do first, though, is go through the problem and decide what the x and the y represent here. So our x here is the number of car seats. And you want to look at units too. So this one just says car seats. It doesn't say hundreds of car seats. Sometimes they will do that. Our P here, which is our Y value, is our profit. And that one says it's in dollars. So now when we plug this in our calculator, in this case Desmond, and we end up with this. They give you domain on these problems. So they're saying our car seats are between 0 and 1700. So if you come over here to your tool and you go to 1700 and 0, and that's our x-axis. Our x is between 0 and 1700. It'll give you a picture. And so now all we have to do is scroll up from there, way up there. Just keep going. We're looking for the max because it said find the max. Way up there. So I'm going to come back over here, change this back to 1700. Change this to 0. And I'm going to make this, it says 58. See what's that? So I'm going to make it 6,000. And then now I can actually find the top. And there's a top. So if you click on the little tool here, you can change the X and Y's until you get what you want. But just clicking on the graph anywhere, remember it shows up. And there it is. There is our max. So 542.87. So there's our graph. Comma. 6314.286. 6314.286. And so again, X here is our number of car seats. So it says find the number of car seats that must be sold to maximize profit. So we have X equals 543 car seats because you can't sell half a car seat or 0.87 car seats. And then our max profit is the Y value. It's that easy. You're just plugging these in and interpreting. So max profit here would be $6,314.29. Okay, let's try one more. So this is the famous box problem that they use a lot. And every time I see this, what we're going to be doing is taking this 10 by 20 box and cutting out the corners of each of these. And so it always makes me think of metal shop. So what I want you to do instead of listening to me, well, you're going to listen to me, but it's to watch a little video of someone making a metal box. It's what we used to do. I did this back in actually in the 8th grade when they had metal shop. I wish they still did. All right, so I'm going to be skipping around in this box and explaining stuff. So here you go. It's a simple box creation. So you can see it's our same shape. He's got a lid here and a base. And you can see there's our sheets. So see there's our squares that they need to cut out. And so he cuts them out. And they end up with this. So as you can see, he cut out this. And that's our X. And that's our X. So right now, this little dotted line here would be 10 take away 2 X's. And this little dotted line here would be 20 take away 2 X's. Okay, so let's see how we make a box out of this. Okay, way too slow. Let's scroll in. All right, so he puts this in a break. And he bends it up. And he does the other side. Same thing. So you can see that's our X. So if you're kind of seeing the box being formed, the height of the box is the X. So that part that we cut out is the X. So you see it right here now? He's making the box. He's got one more side to do. and there's the box. So the height is x, and then like I said before, we had that whole length this way, and all the sides have just been folded up. So if we go back to here, you can see that that was the part that was cut out. And we got this. And so that's our x. And this folds up. That's the height. The width here is that 10 take away 2 x's. And the length is that 20 take away 2 x's. So going back to our lecture notes, we have this situation going on. And so there's a little dotted line here, and he put a dotted line here, and a dotted line here, and a dotted line here. And then he folded along those edges. To make our box. And so that height was x. And the width here of this box is that dotted line, because that's where you fold it along. So it's 20, take away the 2 x's. So that right there is 20, take away 2x. And then the width here was the 10, take away the 2 x's. So we start with a 10 by 20 inch sheet, and they cut out x sheets, x corners, and you end up with this. So what we now need to do is find the restriction. So the way you look at it is this. The smallest side is really what you have to look at when you're cutting. If I were to cut just dead middle, right in the middle, right here, and that would be my big X, that would be a 5 by 5. And if I cut 5 out of 5, I just cut the entire side off. So I know my X has to be less than 5. And you'll see why we want a restriction when we plug this in our calculator. So now we need a volume. And volume is length times width times height. And so our length here is, it doesn't matter the order, 20 minus 2x. Our width is 10 minus 2x times our height. And don't multiply this out. If you multiply it out, it's going to give you a pain in the head, a headache. Because if you make one little mistake, it won't come out right. So what you're going to do is just plug this exactly how it looks in Desmos. So like this, all I did was hit home, and now I'm back here. And then you have to ask yourself, okay, well, what is the restriction here? It's only between 0 and 5. So this is where we're looking at, just here to here, 0 to 5. And you can see it, that's where 0 is. You cut nothing out, you don't have a box. And if you cut out 5, you don't have a box. So that's why the intercepts are. So what we need to do is scroll up like that until we see what our max is. You can only look between 0 and 5. You see there's stuff over here, who cares? It's only here. So we scroll up right here, click on our graph, and there is our max. So 2.113 and 192.45. So 2.113, and I've already forgotten the other number. 192.45. And again, we label everything. So X here is the cutout. It's the dimensions of the cutout, so that guy. And this right here is our volume. So what are we looking for? It says find the X that will maximize the volume of the box. So our X here is 2.113 inches. And our volume then would be 192.45 cubic inches. You always want to put a cube on volumes because we're talking about 3 dimensions. Length, width, height. So we'd have inches, 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 which makes inch cubes. So why is this important? Well, we just now know if we cut out basically 2 1/8 from this little situation, this little corner, fold up the sides, we would get the biggest volume that is possible with this box. And so we just took a box that's 10 by 20 and made a box out of it that would hold the most amount that we need. So it's a pretty cool little problem. All right, let's look at this one. This is another standard one, is you have a river, and this farmer wants to put fence around it for his, what are we dealing with, cows or his herd? So we don't even know. And they give you an area. So our area of this must be 5,000 square yards so that he can feed his herd. All right, but he doesn't put a fence around the river. And so if we label this, we have X, X, and Y. That's 2 variables, which means we're going to have 2 equations. And so you use the area that they have. And our area here is always length times width. So if it's length times width, it's X times Y equals 5,000. And then we also need another equation, and that's the one we're trying to create. So it says what dimensions will use the least amount of fencing. Anytime you see the word least, it means minimize. So that means we're dealing with this function, something that's going to have a minimum value. We're going to decrease and then increase from there. And then it says here minimize perimeter as the basic idea, but it's fence. We take that fencing, and that fencing, and add them together. And so you get 2 X's and a y. That's the perimeter. That's the function we're going to plug in. But if you go to your Desmos, let me clear this out, hit home, and I put y equals, I can't use y, see? Because y is part of the problem. So what you have to do now is you take this one. This is called a secondary equation. It's not the one we want, it's the one we use. So if we solve this for y, divide both sides by x, doesn't matter which letter you solve for, but we're solving for y so that we have everything in terms of x. This now allows us to take this and substitute it here. So we have p equals 2x plus, and then now we can plug that in. And now we're good. Now we have everything in terms of x. Two variables, because we have two dimensions here, an x and a y. We can only have two. So y equals 2x plus 5,000 divided by x. And we already know 5,000 is huge. It's huge. We have 5,000 divided by x here. So we know it's large, so to get an idea of what's going on here, if you plug in 0, it's undefined. We're not going to get anything there. If you plug in 1, it's 5,000. So we know that this is going to be at least 5,000. And we know that's the highest point, right? But why did I plug it in the x? I don't know. That should be 10. The height, the y value, should be 5,000. And there it is. Now it shows up. And so then we know it comes down here. And so remember, if you just click on the graph, it will show you where the minimum is. You're just scrolling along until, oh, there it is. See? So 50, 200 is our minimum value. Just keep clicking on the graph. It will show you where it is. So that's 50, 200. I know it did not look anything like this, but yeah, it's just a slow upward gain. Our x here, we already know is that dimension. So x is 50. So how do you find y? Well, y is, plug it back in. It's 5,000 over x. So this would be 5,000 over 50, which is 100. So we know this is unit-wise yards and yards. So what does the 200 represent? Well, the 200 was from this function. So this is our p, and this is our x. So p here is just the perimeter. So we know we need 200 yards of fencing. And so the question is, all we have to do now is answer the question. It says, what dimensions will use the least amount of fencing? So 50 yards by 100 yards. It just wants the dimensions. But why is this important? Because you don't want to spend a lot of money. And so if you need 5,000 square yards, by doing this, you can see that 200 yards, a 50 by 100, would give you the least amount of fencing, which means it would cost the least. Let's just say that this fence has to be 10 feet high and each yard costs them $100. I mean, that's a lot. It can really add up. And so by finding the smallest dimensions, the smallest length here, you would save money. All right, this last one is just a business problem. And so I've already got it worked out so that you can see what's going on here. So what we're dealing with here is a farmer can get $8 per bushel for the potatoes on July 1st. And after that, the price drops 8 cents per bushel per day. That's a slope right there. Even $8 per bushel is a slope, but it's that price drops 8 cents. Whenever they use the word drops and increase, we know that's our slope that we're dealing with. So it says 8 cents. So we just focus on the money. It says $8.08. So we know that we have $8 per bushel, and then it's going to drop 8 cents per day. And so that we know now is X is per day. We also have a quantity function. And so what's happening is you have a price and a quantity. So right now he can get $8 per bushel, and he has 80 bushels. So if you were to multiply that, he would get $640. But if he keeps farming, he will have more bushels. So instead of cutting the field down and then there's nothing left, he can actually grow more, correct? So if he grows more, his quantity would increase. Thereby, hopefully, his price would increase, his total revenue would increase. But also the price is going to go down. And so we're trying to see when should he sell. Otherwise, you would just keep making as many as you want because price is constant. But price is going down. So we want to find out how many days should he wait before cutting everything. And so our quantity here is 1x, right? It's right here. Sorry, quantity. It's 80 bushels and the crop increases. So you want to just kind of focus on that. It's 80 bushels increases 1 bushel per day. So that right there is our slope. 1x plus $80 is per bushel increases 1 bushel per day. Revenue is price times quantity. See, that's what we're doing here, price times quantity. So if we take the price function and the quantity function and multiply them, what we get is the revenue, the amount that we would get. So every single day, if you were to plug in x equals 1 and 1, you would then get, if I plug in 1, that would be $7.92, and he would now have 81 bushels. So that would give him his revenue. And if he waits another day, that would now mean that he has 82 bushels, but this has gone down another 8 cents. So this would now be $6 and, sorry, 7, it's still 7, it's not a whole dollar, $7.84. And if you multiply those, that would be his revenue. So what we're trying to do is find out when is the optimum time to sell. So we take this function and this function, we plug it in this one function, we plug it into Desmos, and it gives us this. So you can see that his revenue will actually go up here. So at 3 days, he makes $644. At 3.4 days, so let's go to 4 days, he's now at $645.12. At 5 days, and so on. But at 10 days, that's his max. After 10 days, he's losing money. So at 10 days, it's $648. So 10 days, revenue $648. So how long should he wait? 10 days. All right, thank you. Wait, not thank you. It's July 1st. He has to wait 10 days, right? And so this is at right now, it's 0 and 0, $8.80. So 10 days later would be July 11th. So on July 11th, he needs to harvest and sell, and he will make his money. All right, thanks.